Today we discuss the Turing Halting problem invented by Alan Turing in 1936. Before that, David Hilbert's 19th century's famous 19th and 20th century's topmost mathematician David Hilbert, Entscheidung's problem. Entscheidung's problem says within a system, everything cannot be proven truth. At least certain thing you have to take in as a truth, and yes or no answer you cannot come to a halt. So that is Hilbert's Entscheidungs problem. Kurt Gödel in 1930-31 proven that his paper at Princeton University that it is untenable, that is not proven. Then there comes Turing Halting problem. This is Turing Halting problem in 1936. That is unsolvable problems, that is cannot be solved by any algorithm. Same Emil Post, who the correspondence problem in 1946, the post correspondence problems is the dices in the upper regions A, B, and lower A, B, C, D, and there are several dices with several numerators and denominators. You cannot combine a string. I'll come to that. And the Rice theorem, that non-trivial properties of any programming languages on any machine cannot be proven true. That is, I'll come to that. So, and this is post-Correspondence problem I had told. So this is Turing Halting problem, and all these problems, if you can take this undecidable problems, first, though it is alerted by Hilbert and good, but the Turing Halting problems is most what is the central problem, and if all these undecidable problems can be reduced to another undecidable problem like Turing Halting problem to this. So they are, if one can be solved, others can be solved. That is the way. So let's discuss this is Turing Halting problem. That basically says that you cannot tell with 100% guarantee that Turing machine will definitely halt for all cases of time for a program with all its inputs. You cannot say. If Turing machine halts, if in two state, either it accept or reject. But sometimes Turing machine loops, and that is called untrivial property. That is not every cases. So a program with all its different kinds of input, you cannot test the program with all its input that it will definitely halt. Say if you have a program is print hello world, it will definitely halt, but not all program on what programming, like it cannot say that like this. That is the essence of Turing Halting problem. Same here, like most of the cases Turing machine, like here, this is here it is accepted state, that is Turing machine 8 tuple, the Q accept, and this is the Q reject. But some of the cases it will loop around this, and then it's loop and looping, and you will Turing machine will not go to the halt state. Then we call Turing Halting problem. That is the most significant problem of the undecidable problem. It is first discovered 1936, and let's go to the next slide. This is 1946. That is Emil Post correspondence problem. There he has shown that is if any kind of dices, like this kind of dices, and if you have a number of dices, then you have to make it that all the numerators and denominators you can make it with this kind of dices. For these cases it is fortunately it is done, but for not all cases you can. For all type of dices and all kind of this thing you can, like here you cannot make this because always numerator is higher, and maybe some case or other. So this is but you have to try every other tricks, and then you cannot say algorithm. You have to try that it is not definitely you match it. So this is the post correspondence problem. Emil Post, P is an instance of post correspondence problem with a match. The PCP is undecidable. This is the problem I am taking with the Michael Sipser's book, and that is it. In this case, it has been match. And this is the most central thing, all undecidable problems. There's the Turing halting problem. Here it comes to Rice's theorem. Rice's theorem will show that all non-trivial properties of any machine or programming languages cannot be proven true. Like very simple is any two context-free grammar, whether they produce same language, it is undecidable. There is no algorithm. It is so obvious, but in type 3 language is okay, but whenever you go to the type 2 language like context-free grammar or deterministic context-free grammar, even in deterministic context-free grammar, if you give in the two grammar, and that will produce the same strings, language, same string language, but you cannot prove it, they're equivalent. Universal algorithm is not there. So this is called non-trivial properties are there. Even the there are two Turing machines acts the same thing. Whether two Turing machines will always do same thing, you cannot say. This is non-trivial. Non-trivial means if it is go for all the cases, it is called trivial. But some cases it will go produce yes, some cases no. That's called non-trivial properties. So Rice theorem, you can get it from the halting problem. This is tiling problem. Tiling problem like jigsaw puzzle. You have different patterns, and there you have to make a definite pattern, and you're given a tiles of different pattern. You have to make the patterns of a floor pattern, and it is also unsolvable because you have to try and do this. There is no such universal algorithm. Lambda calculus by Tully's guide. This context-free grammar equivalence that I have told right now, that is two context-free grammars are same to the two grammar rules are there. They are producing the same languages. You cannot prove it. You have to show by taking the derivations up to certain state. Then you say that it is a equivalent. So no proof is there. That is the Turing halting problem is the central problem, and it no algorithm for this. And what is Rice theorem says? I told no algorithm can determine if a program exhibits a particular behavior unless it is a trivial property. Trivial means all for all cases. Non-trivial means for some cases it comes with answer, some cases it's not. Halting problem is one of them. Infinite loop detection. So Rice's theorem shows there can be no general algorithm to decide whether these properties for arbitrary programs. Thank you.